changing the olefin distribution from feed 1 to feed 2, which is a feed that is less vulnerable to octane loss. Just a second here. There it is. Feed 2 is much less vulnerable to octane loss. If you change crude or FCC operation, expect your performance curve to move. A common option is to add a splitter that causes the lightest olefins to bypass the desulfurizer. We can show that effect. And here I have now returned back to feed 1. Just a second here, I'm trying to. Okay. This is with a splitter on feed 1, that's the dash curve. Now I'm going to take the splitter out and say, what if we could double the selectivity of the process? That is the sulfur octane selectivity. That might be hard to do in reality, but in the spreadsheet, you can set that and see what effect is, and you get this purple curve, double selectivity. Now, instead of doubling the selectivity, I'm going to set it at 40% improvement, which is more realistic and can be achieved with a new process that's available today. It's offered by Halder Topsoe. And this purple curve now is for a 40% improvement. And by a selectivity improvement, I mean a fundamental improvement in the sulfur octane reaction selectivity that's caused by a change in the process or the catalyst or the conditions. And if you use the new Topsoe process with a splitter, here is that combined effect, the dashed purple curve. So you can see how much octane that would save. And if you are considering a grassroots gasoline desulfurizer, you should consider this new Topsoe process. The performance curve model takes the blood test and reduces it to 10 numbers that pertain to 10 key reaction paths, which are the ones that determine octane loss. These 10 numbers are fed into an olefins model that calculates the changing composition and an octane model that calculates octane from the changing composition. The olefins model and the octane model are, we believe, the best available models for this purpose. And the output is delta octane versus product sulfur, which is the performance curve. And then you can see the effects of the different changes you can make. And you can also do the effects of things like endpoint or cut points, like for endpoint cutting. Now, the model also produces this chart that accounts for octane changes by hydrocarbon type. And this is a field test example. The leftmost red bar shows the loss of olefins, in this case, accounted for 17.3 Ron octane loss. Those olefins became normal paraffins, isoparaffins, and naphthenes, whose octane partly offset the loss from olefins. And then there were some smaller octane effects that involve reactions of aromatics, unknowns, and C14 plus compounds and oxygenates. And the total impact on the far right was 7.3 Ron octane loss. Now, this performance curve model I've been talking about is included with your purchase of Research Report 7, which is the middle one of the three I discussed earlier. So, and this is not a licensed thing. This is, you buy the report, you get the model, and you own it. It's just a one-time cost. All our research reports also include 4 blood tests, so you should just send us samples of your feed and product streams, and we'll get the analysis done and load the model with your own data, and you'll have all the charts I have shown for your unit and more. All our reports also include 6 months of unlimited support by phone and email if you want it. And I hope you can see how valuable this is in the Tier 3 world, to be able to see, understand, and control what is happening in your gasoline desulfurizer instead of it just being a black box to you. And this is something that was seen by some very astute people in my client group back in 2014. They saw their gasoline desulfurizer as an outlier in being a black box process to them. The cat feed hydrotreater and the FCC unit are not black boxes. We have very detailed knowledge and data and understanding of the reactions happening in them. And we use all that knowledge all the time to optimize performance. Why is the gasoline desulfurizer a black box to us, where we can't see and know and understand what's happening inside, and can't use that knowledge to optimize the unit? And that insight by some of my clients was the beginning of our work on this. The performance curve model is a 21st century tool that has been used since 2016 for decision-making on Tier 3 strategy, capital investments, licensor and catalyst selection, process design, feeds, and cut points. And if you have this gasoline desulfurizer, I hope you conclude your engineers and planners should have this tool. With an analysis of your feeds and this spreadsheet, you will be able to see and understand what's happening in your unit and make better performance estimates and better decisions for Tier 3 gasoline. And that is all I plan to present. I want to thank everyone for your attention and participation. And I hope we can get some questions.
George, do you want to go back to the polls, talk about the results?
Yes, let's do the polls. Are you going to do that, or should I?
Well, there's one that you can see on your screen right now. Why don't you discuss that one first?
It looks like we got 8 responses on octane tightness, and it goes right down the middle. Half tight, half not tight, and 25% don't know. Thanks for your feedback on that. Oh, wait a minute. Yeah, okay, here we go. Are you making over 10 ppm sulfur gasoline today? There were 12 responses. 50% said no. 31% said yes. 23% don't know. So a no answer means it's making 10 ppm or under today, 46%. Thanks a lot for, we got 13 responses on that. Okay, thanks for that input from you. Now, what about questions? Do we have any questions?
So there was one comment that was made in the chat. Uchiko Pudi says, to prevent gasoline octane destruction, one option is to pre-treat the cat feed, but that may be very expensive. The other option is to blend it with a reformant to boost the octane. Otherwise, you may run it through a catalyst reformer, such as a CCR, to regain lost octane. These are some thoughts. Unfortunately, we cannot modify catalyst selectivity to preferentially remove sulfur, but not saturate olefins and de-olefins. Olefin saturation reaction is very easy. That is the problem. Can you add thoughts on that?
Oh, yes. I agree with pretty much everything there. I agree that the olefin saturation is an easy reaction to do. It's a lot harder to get the last of the sulfur out. The FCC feed pretreat, or cat feed hydrotreater, that I think is the key for making the manufacture of 10 ppm sulfur gasoline consistent, reliable, and profitable. And it's the refineries that rely strictly on the post-treater, the gasoline desulfurizer, to do the whole job. That is the difficulty that we have in the US. So I don't know what whether this question was suggesting that cat feed hydrotreaters are good, but I believe they are. And I think the big weakness in our infrastructure today for making Tier 3 gasoline profitably is that we have many refineries that don't have a cat feed hydrotreater and still want to be able to vary their crude slates and want flexibility. And for those refineries, they're going to have a much more constrained situation with 10 ppm than with 30. I think there was something in the middle of that question and I forgot. Could you reread it quickly, Becky? I think we have time. Reread the question. Or was that Marlies?
No, that was Becky. No problem.
Okay.
It says to prevent gasoline octane destruction, one option is to pre-treat the cat feed, but that may be very expensive.
Right.
Another option is to blend it with a reformant to boost the octane.
Yes, that is something that refiners are doing, but it costs money to replace the octane that you destroyed in the gasoline desulfurizer. So it comes at a cost. I think that may be the point I missed. Go ahead and read the rest of it, Becky, please.
Okay, it says, otherwise you may run it through the catalytic reformer such as a CCR to regain lost octane.
Right.
Fortunately, we cannot modify catalyst selectivity to preferentially remove sulfur, but not saturate olefins or diolefins. Olefin saturation reaction is very easy. That is the problem.
Well, I don't think the industry is at the ultimate in terms of selectivity that can be achieved in terms of getting higher levels of desulfurization with less octane loss. There is potential to improve that with catalysts and with processes. I don't think there has been a big incentive to do that in the past because the post-treater hasn't really been a stressed out limiting unit, but now it is going to be. And I think there will be improvements in catalysts and technology, like I mentioned, the topsoil process, that will enable improvements over time. I think I answered all of that. That was a great question. Thank you.
Uchi, would you like to unmute yourself and add to that discussion? I don't know that I'm doing you justice.
Good morning to everybody. This is Buchi Galapudi. I'm from Bantrel. We are an EPC company in Alberta. I'm from Edmonton, Alberta, Canada. I have worked in cat crackers in the past and also the catalytic reformers, the platformers and CCR. And I'm very concerned about this octane loss from gasoline. Gasoline desulfurization for meeting the regulatory requirements, that actually results in, as explained here, it was very well explained by the presenter here. I think that is George. Is it George?
Yes, yes.
George, and actually thank you very much for a wonderful presentation you made. So my ideas, of course, I just wanted to share with you. We used to run in our cat cracker the pre-treated feed. So there was no need for us to do gasoline desulfurization. That's a post-treatment. We didn't have that. But all the FCCs are not like that. Mostly you're trying to feed the atmospheric residue, and so if you all kind of junk you can feed into the cat cracker. So if you're doing that, the hydrotreating is a big challenge. So I think, as you mentioned, George, it's if we can develop catalysts with better selectivity to do the hydro desulfurization rather than the olefin saturation, that would be the best way to go, to minimize the cost and be focused only on gasoline kind of thing instead of trying to pre-treat the feed. So those are the comments I have. Do you have any questions or comments for me, George?
Yes, I would ask, do you have any experience in changing the catalysts in a unit at all?
No, I'm actually a process engineer.
Okay.
I have dealt with many catalyst vendors for different catalysts like hydrotreating, hydrocracking, hydroprocessing in general, and also the cat cracking and platforming. I dealt with many vendors, many catalyst suppliers, but this is something, the gasoline desulfurization catalyst, something still needs to be developed. I'm sure people like Topso or these people must be very actively looking at it. I think that would be the answer going forward.
Yes, I agree. Well, thanks a lot for all your input, your questions and comments. I think that I mentioned the gasoline desulfurizer being sort of a black box, and it hasn't really been stressed in the United States. It's done its job just fine. Many gasoline desulfurizers ran on their first load of catalyst for 10 years. That's a situation that doesn't produce a whole lot of interest in optimizing the process. I think if you look at the processes that are really important for the bottom line these days, now we have this new one on the list, the gasoline post-treater, that before was not very important. Now it's like you've got a new potential handcuff on your FCC process train, which is the main place where you can manipulate things and make money. And you don't want to be constrained by a little low pressure naphtha hydrotreater. And I really believe that once people pay attention to this process and really work on it, we're going to see advances in it, just like we did with cat feed hydrotreating, like we did with diesel hydrotreating, and like we continue to see in FCC and reforming. So I think this process is really quite early in its development path and is only now entering the picture as something where people really are going to be interested in improving it. So I think we're on the same wavelength, and I really appreciate your comments. Thank you.
Okay, thank you.
Mm-hmm.
George, the next question is from Bernard Robinson, and it is, what is the more critical for octane loss? Percentage desulfurization or absolute sulfur in the product?
Okay, it's another
10 ppm.
Another great question. You notice that on my charts, I use absolute sulfur, not percent desulfurization. That's because I believe that when you get down to 10 ppm around there, I know there are certain compounds that are the limiting ones that you have to get out. A lot of the other sulfur in there doesn't matter. So we find that the absolute sulfur down in this range of operation, where you're talking 30 ppm down to single digit, you want to be looking at the absolute sulfur, not the percent desulfurization. If you have, to correlate olefin saturation and octane loss, if you have removed 95% of the sulfur and it was all very easy, that's irrelevant. What's really relevant is how much of the critical compounds are left. And that's why our chart is against absolute sulfur rather than percent desulfurization. That's a great question. Thank you. Bernard, any comments from Bernard? I think if you look at charts of percent desulfurization versus octane loss, octane loss versus percent desulfurization, or olefin saturation versus percent desulfurization, you'll see a huge amount of scatter in them. That's because that chart doesn't do any factoring in of feed effects, which are very important, and other things that affect that curve. And you saw my curve bounces up and down a lot. We know what's causing those changes because we understand the chemistry going on. If I was just charting total percent desulfurization based on total sulfur, I'd be missing a lot. The next question, I see one up here, Becky. Is that where I should go?
Well, so there was a comment in the chat maybe about what you were just talking about. It says, what about aromatic extraction to generate a high sulfur rich stream with minimum olefins that can be hydrotreated?
Yes, that's an alternative approach that is available and should be considered by someone who's going to invest money in this. We have not done research on it. I think the licensors who offer that technology have good capability for estimating it. So it's a different category. I should have made clear, I guess, I'm talking about conventional fixed bed desulfurization, selective desulfurization here. The extraction is an alternative route that I think works. It allows you to save octane like you can with this process. It's less commercially developed in terms of number of references, but it's something I have no reason to not consider that as an alternative if someone's going to invest money.
George, this
Yes.
is Bucci Golapudi again. If I make a comment here, the
Yes.
aromatics saturation is a very difficult reaction. It's a very highly exothermic reaction, and that reaction doesn't take place so easily. My understanding is when it comes to hydrodesulfurization, olefins and diolefins are easily saturated and sulfur is removed very easily from those compounds, but not from the aromatics. So I'm not quite sure. So if you have a catalyst like maybe cobalt molybdenum catalyst instead of nickel molybdenum, or which is activated by maybe vanadium or something other, if you have that kind of catalyst, a cobalt molybdenum catalyst, it will probably hydrotreat easily the sulfur removal, but probably not do the aromatic saturation. Only olefin saturation will take place. That's my understanding. I don't know if you have some comments on that.
Yes. Well, I think we might be talking about a couple different things. I was answering the question thinking about extraction, not saturation. Okay. So I don't know, maybe I didn't answer the right question, but I agree that aromatic saturation is not a reaction that occurs much, if at all, in this process because the conditions are so mild in this process that I talked about. But there are some reactions that happen with the aromatics, and we can see that because of the detail that we get in our analysis. So I guess my contribution to that discussion would be to say that the aromatics can become an important participant in the reactions that go on in this unit, but it's not going to be the ones we think of that go on like in a cat feed hydrotreater, which is aromatic saturation. You can't get that reaction to occur at the kind of pressures that this unit operates.
Yeah, I'm saying in the context of removing the aromatics, because is it worth doing that? It will be economically, may not be justified, because even if the aromatics are there, they're not getting saturated anyway.
Yes, I see what you're saying. Yes, yes. Okay, yes, I see what you're saying. So that's even a third item. Okay, yeah, thanks for that.
So George, one of the participants, Mr. Janad, has raised his hand. Sir, would you like to unmute yourself and ask your question?
Hi, George.
Hi.
George, I would like to add that we would like to retain aromatics because they have got a very big contribution to the RON.
Oh, yeah.
So,
right.
So I don't think it is, and for the conditions that exist in these naphtha HDS units, we have got the conditions are such we have zero aromatic saturation, and we would like to retain maximum aromatics to preserve the RON.
Right. I agree. I mean, they have a huge benefit there to the octane. Thank you.
Okay, we have another question from Mr. Venkatraman. What is the most frequent improvements done based on your models?
Please repeat that. What is the most frequent improvements? Say.
What is the most frequent improvements done based on your models?
Okay, well, the things, endpoint cutting is a typical optimization step that people can take. And we can simulate that with the performance curve model just by varying the endpoint, the data in the blood test that correspond to the endpoint. Also the sulfur speciation, which I didn't talk about. But when you are getting down to 10 ppm sulfur, the sulfur speciation tells you exactly what sulfur compounds are the ones you want to get out. And a lot of units have splitters, and you want to be able to optimize how much light naphtha you take out. So people look at these two analyses, the blood test, hydrocarbon type analysis, and the sulfur speciation, and optimize their cut point so that they can get the sulfur they need to down into the high severity part of the process. Of course, as you do that, as you push more sulfur down out of the light naphtha and get it into the sulfurizer, you get the sulfur out, but you're also pushing more olefins down there. And they're usually the olefins that are in high concentration, and so you lose a lot of octane. So there's a good optimization that you can see and do with the model for the cut point on the light and heavy naphtha if you have a splitter, and the end point. I think those are common ones. Now, people I think can also get an indication of, they look at where they would like to be in terms of start of run activity and start of run temperature. What is the trade-off between having a more active catalyst and being able to run at a lower temperature? We can do some of that type of simulation. And then a lot of it is done for capital investment alternatives. And for design. Our model has been used quite a lot to help design units. It's a lot easier to do that when you can see the chemistry going on than when you just have sulfur, octane, and bromine numbers. So those are our three: endpoint cutting, splitting optimization, and investment alternatives.
Okay, we have another question from Vivek. Does a better catalyst operate at a lower temperature to retain the olefins while having sufficient desulfurization, or it operates at the same temperature, still olefin saturation is lowered?
Well, I think the answer is you like to have higher desulfurization activity relative to the olefin saturation activity. And if you have that, either one of these two things is available to you. So if you have a catalyst that's more active, or if you have a catalyst that's more active, that means you can start it at lower temperature, okay? If you have a catalyst that's more active, it also means that if you run at the same temperature, you'll saturate less olefins. So either one of these alternatives goes back to the question of what is the relative rate of desulfurization compared to olefin saturation. And as someone said earlier, the olefin saturation is the easier of the reactions. So when you're designing a catalyst, you might do it by reducing the activity for hydrogenation of olefins. You might do it by trying to increase the activity for desulfurization. But what's important is the relative of those two. And then if you get that better selectivity, you have a choice. You can run it at lower temperature, or you can run at the same temperature and reduce your octane loss.
Okay, well, we've covered all of the questions that have been submitted. Would anybody else like to unmute themselves and make a comment or ask a question? Okay, George, any final thoughts before we close?
Yes, since we have a couple minutes, if anybody wants an offer letter for any of our reports, please contact me. And I have my email and my phone number here, or of course, contact me anytime with any more questions. So I think you can still see my screen with my email address is george.hoekstra@hoekstratrading.com, and the phone number. This is
my question is, would you be able to make this presentation available to the participants?
What I'm going to do is, over the next week, I'm going to put the basic content on YouTube. And Becky, is there a way that we can then notify the attendees of that?
Yes, of course.
Okay, so within a week, I will put this up on YouTube, and then you can watch it. It'll probably be in 3 little segments. Is that okay to the questioner?
Okay, thank you.
Yes. That's all. I just want to thank everyone for your attention, and thanks to REFCOMM. That's all. Thank you.